Hello everyone. The title of our paper is Adaptive Data Rate-Based Congestion Control in Vehicular Ad Hoc Networks. I'll be starting the presentation by giving a basic introduction about the vehicular ad hoc networks. I will also mention our research objective, which will be followed by the proposed approach explanation. I'll also mention the parameters chosen for simulations and the results obtained. Finally, I'll be concluding the presentation by mentioning our future work possibilities. VANET refers to a network created in an ad hoc manner where vehicles and other connecting devices come in contact over a wireless medium and exchange useful information to one another. VANET is a variation of MANET, the mobile ad hoc networks. MANET comprises of nodes which communicate with the central network and where nodes are equipped with networking capabilities. VANET, on the other side, has emerged as a challenging and more liable variation of MANET. The freedom of nodes to enter or leave the network in VANET calls for different routing protocols than MANET. This inter-vehicle communication leads to exchange of information so as to increase traffic efficiency, detect road conditions, decrease collisions, detect emergency situations, and overall increase the efficiency of the network. Following are the characteristics of VANET. Firstly, the dynamic topology. The speed and direction of the vehicles changes constantly, thereby resulting in high dynamic topology. Next comes the intermittent connectivity. Connectivity between devices changes very frequently, like connection between two devices exchanging information can disconnect anytime. The reason behind frequent disconnection is high dynamic topology. Next, the mobility patterns. A large section of vehicles follow a certain pattern to move, which is generally a function of traffic signals, speed limits, highways, streets, road conditions, etc. These patterns, when observed, help in the creation of routing protocols for VANET. Finally, the onboard sensors. VANET assumes that the nodes are seldom equipped with onboard sensors, which are capable of transmission of information to other devices or nodes. Following are the two basic types of applications. First is the safety-oriented application. These applications are developed to increase the safety of road and other users. This area plays a crucial role in saving lives of human beings, as majority of accidents and loss of lives takes place because of collisions or lack of safety while driving. Some of the applications include the cooperative driving, collision avoidance mechanisms, and traffic optimization techniques. Next are the infotainment applications. Such applications facilitate the drivers and other users by providing various messages that aim to offer entertainment-related and other information to them, such as information regarding nearest car repair station, coffee shop, parking lots, etc. Some of the applications include the cooperative applications and the global internet services. The VANET environment contains the following components: vehicles and their onboard units, the roadside units, and other infrastructures like traffic signals and central authorities. The following are the VANET communication types. Firstly, the in-vehicle communication. It detects performance of the vehicle and determines factors such as driver exhaustion or drowsiness. Determination of such factors and their extent is crucial for public safety as well as for driver safety. Secondly, the vehicle-to-vehicle communication. This kind of data exchange takes place between different vehicles so as to assist the driver by informing them about warnings and other critical information. Vehicle-to-vehicle communication does not rely on fixed infrastructure for data exchange to happen, and it helps in dissemination, safety, and security applications. This research work focuses on vehicle-to-vehicle communication. Next, the vehicle-to-infrastructure communication. This kind of communication takes place between mobile vehicles and roadside infrastructures in order to gather data. It provides updates related to environmental sensing and monitoring, such as real-time traffic update or weather update. Finally, the vehicle-to-broadband cloud communication. This allows communication of vehicles over broadband connections such as 3G or 4G. This enhances driver assistance and vehicle tracking, as a broadband cloud may contain more of traffic information and other data. The challenges of VANET are, firstly, the mobility. Ad hoc networks comprise of mobile devices and other devices as nodes which have limited mobility, whereas in VANET, the mobility factor of nodes is very high. Vehicles come and lose contact in a matter of seconds as speed is measured in miles per hour. Exchanging information in such a small amount of time and with such highly heterogeneous nodes is an open research issue. Data administration and storage. Any number of vehicles or other stationary devices can participate in a VANET. For large-scale VANETs, number of nodes participating in a VANET can increase up to millions, which will in turn generate a large amount of data. Monitoring, managing, and storing such a large amount of data is still a challenge. Security and privacy. VANET is an open network where any node is allowed to join the network. There is no certain mechanism which can ensure the trustworthy nature of the nodes. Therefore, security becomes a major concern for researchers, as communication between the nodes happen over a wireless medium, where any node can transfer malicious data and may cause significant harm to other nodes. Heterogeneity and standardization. The nodes participating in a VANET are highly heterogeneous in nature, such as cars, buses, trucks, roadside units, and traffic lights, and other nearby computing resources. Such diverse nature of nodes or vehicles are different modes of communication, and every node follows its own set of communication mechanisms. Dealing with such high-density networks and their varied modes of communication requires standardization of protocols via which nodes can communicate with any node on the go. Routing protocols. Traditional routing protocols are not appropriate for a VANET, as nodes participating in a VANET have very high mobility, and thus they can change the network topology in a matter of seconds. Channel congestion. The 802.11 wireless protocol is currently the only protocol for low-latency vehicle-to-vehicle safety communications in VANET. All the safety messages are transmitted with 802.11p, which uses carrier sensing multiple access with collision avoidance to reduce collisions and provide fair access to the channel. CSMAC is a contention-based random access protocol that can cause simultaneous transmissions, that is, packet collisions, which significantly lower the communication reliability. The important packet collision avoidance mechanisms like the request to send and clear to send handshake are disabled in 802.11p MAC layer, resulting in hidden terminal problems. The three important consequences of high channel load are successful packet receptions decrease, and transmission delay increases with increasing message generation rates. Effective transmission range decreases under high channel load conditions. Communication range of a transmitter decreases under interference due to hidden stations or simultaneous sending. Congestion control approaches. Congestion control aims to improve the VANET network's performance by reducing the packet delays and losses, increasing throughput, etc. This section discusses fundamental concepts in the area of VANET congestion control. Congestion control algorithms use different approaches to determine and adjust the transmission parameters. They are proactive. These approaches reduce the channel load before the congestion is detected on the channel. Optimization algorithms are used to select the required transmission power or rate to limit the congestion. Data generation patterns are used for the estimation of transmission parameters. Reactive. These approaches reduce the channel load after the congestion is detected on the channel. Channel congestion status is gathered to determine the actions to be taken. Hybrid. These approaches combine both reactive and proactive strategies for controlling channel congestion. Our research objective was to ensure that the channel load of the network does not exceed the maximum threshold, reduce the congestion happening in the network, and finally to reduce the total number of packets lost, aiming for accurate information transfer of the safety messages. Our problem statement was to implement a congestion control algorithm which effectively maintains the channel load from exceeding above the channel threshold for the transfer of safety messages. Proposed approach. There is a need for suitable data rate selection for addressing trade-offs like higher data rates can reduce signal strength. It also limits the transmission range, making the packets unreachable to distant vehicles. Lower data rates increase the channel load due to slower packet transmission. Using the same data rate at different vehicular densities causes wastage of resources and leads to poor performance. The overall motto of the proposed approach is to maintain the CBR between high and low channel thresholds to achieve more packet deliveries and maximum throughput. It consists of two parts. Part 1 is for selecting the optimal data rates when the current CBR of the network falls below the lower CBR threshold. Part 2 chooses the optimal data rate when the current CBR of the network goes above the higher CBR threshold. A list of data rates are given as input to the algorithm. CBR of the network is monitored every second. Default value of 6 Mbps is chosen as the first data rate level to start with. High and low CBR thresholds are chosen as per the network conditions. The motive of the algorithm is to maintain the CBR between the low and the high channel thresholds of the network. Proposed approach Part 1. When the current CBR of the network falls below the low channel threshold. The algorithm looks for the best possible data rate level from the beginning of the list to the current level in use. That is, the algorithm looks for the lowest possible data rate, since the list is in ascending order. The quotient of the current level and the new level is multiplied with the current CBR of the network. The resulting value is checked whether it exceeds 95% of the high channel threshold value chosen beforehand. If it does not exceed, then that particular value is chosen as the best possible data rate of the particular time of the network. Let us look at the illustration. Let us assume the low and high channel thresholds to be 0.3 and 0.5 respectively. Since the current CBR of the network falls below the low channel threshold, the algorithm checks with 3 Mbps whether it will be the next possible data rate. The current level by new level is 6 by 3, which gives 2. Let us assume the current CBR of the network to be 0.1245. 2 times 0.1245 gives 0.249 as a result, which is well below the high channel threshold. So 3 Mbps is chosen as the next data rate level of the network. Proposed approach part 2. When the current CBR of the network goes above the high channel threshold. The algorithm looks for the best possible data rate level from the current level in use till the end of the list. That is, the algorithm looks for the highest possible data rate, since the list is in ascending order. The quotient of the current level and the new level is multiplied with the current CBR of the network. The resulting value is checked whether it exceeds 95% of the highest channel threshold value chosen beforehand. If it does not exceed, then that particular value is chosen as the best possible data rate level at that particular time of the network. Let us look at the illustration. Let us assume the low and high channel thresholds to be 0.3 and 0.5 respectively. Since the current CBR of the network goes above the high channel threshold, it checks with 9 whether it would be the next possible data rate. The current level by new level is 6 by 9, which is 0.6. Let us assume the current CBR of the network to be 0.5626. So 0.6 times 0.5626 gives 0.3375, which is below the high channel threshold value. So 9 Mbps will be chosen as the next data rate level of the network. The simulation setup. Different parameters and 3 different traffic scenarios were considered for simulations. The traffic scenarios are named as normal, stationary, and fast environment. The simulation time was set to 120 seconds for all the simulations. The road length was 1000 meters for all the 3 different traffic scenarios. The BSM generation rate was set to the default value of 10 Hz. There were 2 different BSM sizes chosen for the simulations, first being the 256 bytes and the second being the 1024 bytes. Similarly, the chosen beacon intervals were 0.1, which is 10 messages per second, and 0.01, which is 100 messages per second. The length of the vehicle was a constant 2 meters for all the traffic scenarios. The vehicle speed was set to 50 km per hour in the normal traffic environment, 0 km per hour in the stationary environment, and 100 km per hour in the fast traffic environment. 80 vehicles were generated during the simulations in all the traffic scenarios. Comparison with constant bit rates in a normal speed environment. In the setup simulation, the proposed DSCA approach was run alongside different bit rates such as 3, 6, 9, 12, 18, and 24 Mbps. The evaluation parameters considered were the average CBR and the total number of received packets. The first case with 256 byte packet size and 0.1 beacon interval is considered to be a low congestion scenario since only 10 messages are generated per second. The other 2 cases are considered to be high congestion scenarios since 100 messages are generated per second. In the first case, the average CBR decreased as the data rate increased. Yet the proposed approach stuck with 3 Mbps. The efficiency of the proposed approach becomes evident with the received packets. The total number of received packets decreased as the data rate increased. This was because of the low signal strength which the higher data rates can cause, making the messages unreachable to distant vehicles. In the other 2 cases, the average CBR decreased as the data rates increased. The proposed DSCA approach results in the best case average CBR, even though it did not achieve the lowest average CBR, which the 24 Mbps did. In terms of received packets, the count increased as the data rate increased, and the proposed DSCA approach was considered to get the best case count, resulting in the optimal usage of resources. Similar to the simulations of the normal speed environment, in the first case the average CBR decreased as the data rate increased. Yet the proposed approach stuck with 3 Mbps. The efficiency of the proposed approach becomes evident with the received packets. The total number of received packets decreased as the data rate increased. This was because of the low signal strength which higher data rates can cause, making the messages unreachable to distant vehicles. In the other 2 cases, the average CBR decreased as the data rates increased, and the proposed DSCA approach resulted in the best case average CBR, even though it did not achieve the lowest average CBR, which 25 Mbps did. In terms of received packets, the count increased as the data rates increased, and the proposed DSCA approach was considered to get the best case count, resulting in the optimal usage of resources. Similar to the results of the normal and stationary speed environments, in the first case, the average CBR decreased as the data rate increased. Yet the proposed approach stuck with 3 Mbps. The efficiency of the proposed approach becomes evident with the received packets. The total number of received packets decreased as the data rates increased. This was because of the low signal strength which the higher data rates can cause, making the messages unreachable to distant vehicles. In the other 2 cases, the average CBR decreased as the data rates increased, and the proposed DSCA approach results in the best case average CBR, even though it did not achieve the lowest average CBR, which 24 Mbps did. In terms of received packets, the count increased as data rates increased, and the proposed DSCA approach was considered to get the best case count, resulting in the optimal usage of resources. Comparison with the existing approaches in a normal speed environment. In this set of simulation, the proposed DSCA approach was compared with two other existing approaches, namely data rate based decentralized congestion control and transmission data rate based decentralized congestion control. DRCA1 had high and low channel thresholds of 0.5 and 0.3 respectively, and DRCA2 had 0.4 and 0.2 as high and low channel thresholds. From the tables, it can be understood that the proposed DRCA approaches achieve the best possible results compared to the existing approaches. Similar to the simulation results of the normal speed environment, it can be understood from the tables that the proposed DRCA approaches perform better than the other two existing approaches in terms of average CBR and received packets. Similar to the simulation results of the normal and stationary speed environments, from the tables it can be understood that the proposed DSC approaches perform better than the other two existing approaches in terms of average CBR and received packets. Conclusions. In this paper, we proposed and analyzed a new approach called DRCA for adapting the bit rates used for BSM transmission. DRCA showed a significant improvement when compared with constant bit rates and existing data rate control approaches. When the CBR is balanced, it helps in achieving more successful packet receptions. Future work. It would be exciting to see how transmission power control could affect the proposed approach. Accuracy of the CBR function using the proposed approach could also be improved. Thank you.